Hey, welcome to the STARS presentation for the monthly meeting in February 2022. We have a great presenter today. We have Chuck Abrams, K9 Charlie Foxtrot Alpha out of Houston, Texas. And he has a special guest he'll introduce in just a minute. Chuck is a technical partner at ABR Industries. They've been in the wire and cable industry for 31 years with wireless control systems, HTV, and industry markets. They do a whole lot in the amateur area and the commercial area. They have 15 employees. And without further ado, let me introduce Chuck. And Chuck, you can introduce your special guest when he comes back. So welcome, Chuck.
Well, thank you, everybody. I appreciate the time. Like I said, yes, my name is Chuck Abramson. I'm with ABR Industries. Let's see here. Can I share my screen?
Where'd that be able to?
Yes, please. Where did the screen share go?
Be on the Zoom control panel for you.
There we go. And
okay. And Mark's coming back too. You want to introduce Mark?
Yes. So that's done. And
what's Mark's call sign? Also, what's Mark?
Yeah. Also with me today is Mark, my father, who started the business. Sorry, I went into the screen share real quick, but Mark is just going to have a few minutes with us today. He actually has to go to deal with something else, but wanted him to say hi to everybody. People always like to know how these businesses start. And between my father and I, we've been doing this for over 30 years. So we've definitely got a long time of doing this, a lot of experience. And what would have happened if Mark didn't kind of pull it up by the reins and get things going? So I always like to introduce him and kind of just share a little bit of knowledge and tidbits. So just want to say hi.
Hi, everybody. Been in the cabling business since 1975. And prior to that, my uncle was in it, and that's how I got started at Annixter back in the day. So been at this a long time.
So with that, I'll just get started with the presentation itself. So
great to have you, Mark, with Chuck. Thank you.
Thanks, guys.
Thank you.
So like I said, just a quick blurb about us. Today we'll spend some time, going to go through a little bit of history, little terminology stuff that's always helpful to know. It's not the necessary things of knowing inside and out. You know, wiring cable, sometimes the best analogy from a marketplace standpoint is a lot like tires. The more you use them, the harder you use them, the rougher you are on the terrain, or not as rough, can really vary between different products. But talking through some materials as well as some basic logic. So some of it's probably review for most, but it's always just good to set a baseline. Then I'll get into the popular types of cable for amateur radio. We sell a great deal commercially as well, but really want to focus on the ham radio side of things. You know, get to the chase, maybe what's really the most important thing and why. And then talk through some of the popular connectors, and then kind of give a little bit of other information. So talking through coax, you know, people always say it's really simple. What is coax? It's the center conductor with a dielectric over it and the shielding. And that's probably as bare bones as coax ever really was. But in reality, the transmission line does so much more for us today. It's used in networking, it's used in amateur radio, high-speed data buses, cable TV, you name it. Coax really has a lot of different places and a lot of different applications. Some of you probably or may know it was originally conceptualized back with Oliver Houseide. And the whole idea there was to try to get rid of noise that was being developed, because using twin lead can be unpredictable if the distances change or the twin lead gets absorbed due to metal or other environmental issues. So essentially, he came up with the overall theory and patented the design. And realistically, what he patented was Heliax. So if I had to explain it in just generic terms, he really was kind of the creator in the design of Heliax. The coax that you see today that was woven is because we actually used another industry, which was the garment industry, to develop coax cable as far as weaving braid and doing other things with the plasticizers. So just to jump in real quick, impedance, everybody understands 50 ohms, 75 ohm for video, and then 93 ohm for networking. But it really comes down to coming up with a simple equation of inductance and capacitance, and looking at the distance between the center and outer conductor, which is the braid itself. So I decided to take a little bit of a cheat example, which is always 213. It's kind of a bare bones cable, but for most people, it's easily identifiable. We took the dielectric constants, which is, I'll show a little bit later, dealing with the inverse proportion of the speed of light, and what we know about the center conductor and the braid distances. And when you play with the math on the bottom of the page, you come up with 50 ohms. And reason being is coax has tolerances. So for example, 213 technically comes in at 49 ohms with a tolerance of plus or minus 2 ohms. But if you look at like an RG8X, that design is actually a 52 ohm with a plus or minus of 4 ohms. So as we play with smaller sizes, the impedance gets more challenging. And as we go larger, it can change, but it's not as difficult. A couple of other pieces, velocity propagation. It comes down to looking at what that velocity looks like in terms of losses and doing matching, but air is always ideal, but it's not always realistic because air dielectrics can crush, they can get moisture buildup into them, they can have other environmental issues. So what was kind of developed was these other three dielectrics that you see here. One is the foam type of dielectric, which came out in the late 60s, early 70s. And the foam dielectric made it nice because if you look at this compared to a 1 gigahertz signal, you still get a fairly decent performance out of the dielectric, which means not as lossy. Teflon or PTFE is still very popular today with a lot of you guys. I know people use them in repeater systems, people use them in government applications. The government still uses it for satellites, so Teflon is still available. And then at the bottom there is the old PE, which is the 213. But 213 still has a place. And when I talk about the different cables, I'll kind of describe a little bit of why 213 on HF with high-powered applications can still be a viable option. Couple of other pieces when we're working with the velocity is the velocity of propagation comes down to the speed of light and helps us understand the dielectric and the insertion losses that are associated. But it all comes down to how we measure the time delay. Some of you may have TDRs, and looking at those and looking at what the time delay is based on the TDR's performance. One other piece is frequency cutoff for cable. Some people don't realize, but depending on the size and design of the cable, you can look at different cutoff frequencies. Not saying I recommend 213 at 12 gigahertz, but technically it is still viable. We actually still use 213, believe it or not, for receive sites with NOAA for weather satellites. So there is still places where you can go much higher than what we think for hams is its original intention. And then one last piece on cabling is data sheets have cutoffs typically about 6 to 8 gigahertz. And the reason being is the original test equipment on a lot of this stuff that we used was BNC types, which is limited up to 6 gig. And it also depended on the size of the coax that was being tested. But for a lot of manufacturers, we decided to stop there. It wasn't like it was the end of the world, but from a test performance baseline as a group, we decided that that was a good starting point. So for a lot of data sheets on standardized coax, you'll see it just limited to 6 or 8 gig. Here's probably the one question that I constantly get asked by people is, okay, what is my loss? What does the attenuation look like? So when I figure that out based on your frequency, I already know what the skin and dielectric loss is of the different cables and can just look at a simple calculation, match it up with the frequency, and then generally try to round up a little bit just to be fair. So for example, here that you see is using the dielectric and skin loss of 213 and figuring it out at 30 megahertz. One other piece is the reason why we pick the higher frequency, of course, is try to take the worst case scenario because things always get better from there. So it's the little brightest sunshine that I always get to share with people as things improve as the frequency changes. A couple of other pieces on return loss. This is from a perspective of testing. So I know some people get hung up on this, but when we look at test parameters, the reason being is even though 1-to-1 is ideal and 1.5-to-1 is very good, the connector industry, and this was done by Amphenol and Huber-Suner, decided that a 2-to-1 test ratio was still the best test ratio they should get. Things can get better, and obviously things can get worse. But the decision was made many, many years, even before me, that that was a good test standard to work off of. So test reports usually that you see out there start with 2-to-1 ratios for the connectors themselves. 3-to-1 obviously gets lossy, 4-to-1 starts to get system issues. Anything that you're above that obviously clearly needs a tuner, but just to give you some insight onto pieces that we look at there. Jumping a little bit to more of the mechanical side of things, the material. Obviously, we talked about the makeup, but when we look at center conductor material, there's always trade-offs. So let's talk a little bit in those terms. One is copper is obviously by far most popular because of performance and price. Now you can do little tricks to improve the copper's conductivity. You can tin it. It'll add 10 to 20% of the cost, but it improves the performance, usually about 30 to 40% as far as the conductivity curve goes. Solid center conductors are generally lower loss because of the way it's designed, and obviously there's no capacitance between the conductors, but there's limited bend radiuses, and you can only flex the material so much. Now, as we'll talk a little bit later, but just to get into it now, obviously with skin effect, you can also copper coat things. So like the LMR type products, you can copper coat an aluminum product, get the performance that you want out of it, but with a number of flexes, which is, to be honest with you, 50 to 100, the microfractures that get caused in there can change the skin effect. That's not to say go panic and run out and change your coax right now if there's some slight twisting or maneuvering, because usually we look at the skin effect at 1 gig and above. So at lower HF frequencies, it's not as critical, or VHF or UHF even. And then also stranding obviously can help our bend radius and improve the life of a different coax. Dielectrics, showed the velocity in the earlier page. Solid poly was kind of the first commercial standardized product. Came out back in the 1930s when they were starting to learn about how to extrude it. And then they decided that there was only so much limitation that they could put as far as power through this. So they decided to look at other viable sources. And when Teflon PTFE became a commercially viable source, before that, the government got their hands into it and started to focus on that product. And then from there, we learned that it was good, but it wasn't great because even though you could use them for satellite, it was still a little bit too lossy. So taking foam, which is a chemical-based foam, the old stuff that you see out there, and creating that increased the velocity to a solid 75% and above. And then we got even trickier with it. We decided to put nitrogen in line and experiment with it, and could get into the high velocity products you see today, which is the 80 percentile plus. So kind of a little quick overview of that. This is where coax really started to shine as a viable product for everybody, which was in the shielding. By waving the braid, we could increase the coverage, and we could get braid coverages up to 95 to 97 percentile. Just depends on the way it's woven and the design and the number of wires. Typical wire braiding is anywhere from 26 to 32 wires that are woven into a V-shaped fashion. And then foil with the aluminum tape and the bonding techniques that were out there can obviously increase the shield effectiveness. Still today though, corrugated copper products, which is the Heliax items, are really the highest level of coverage. But the challenge there is because of the copper and how pure it's got to be with the moisture and the migration. Some places have replacement cycles of just at about 10 years before the conductivity curve gets too high or too low, sorry, and then requires a change there. You know, you can get creative with your shielding too. As you can see, that's just a standardized braider that you see in the picture. And there's the foil, and the braid can be different fashioned in different lengths and different ways, so that you could triple weave something or double weave it. Some people are familiar with 214 and 223, which is a silver-based product. That's where those come in. Some of the higher foil and braid combinations are generally used in computer applications or in some places where they're 18 gig and above, but they're extraordinarily expensive. Jacketing, you know, there's a generic jacket PVC. It can come with or without a UV inhibitor. For most hams, you really want to have a UV inhibitor being outside. Stuff gets baked, especially where you guys are at. But then you can get other things into it. So like type 1 is just a standard UV. Type 2 means that we add another compound, which makes it non-contaminating. What does that mean? Realistically, what it means is that it's resistant against certain chemicals like salt and other basic alkalides. And then we can get really nuts and do crazy things like a type 3 jacket. Now those are general specifications in regards to chemical resistance. So for example, my 400 material I make with a type 3 jacket because it's designed to have a sheen that resists against oil and gas, being here in the oil market in Houston. So it's one of those types of things that allows us to do even something more and get a little bit more creative to resist against the environment that it's being placed in. A little bit more background. Just so everybody understands, all coax in the US was really derived with an RG number, and the process was really started with the 1900s with the government. There's a rhyme and a reason for a lot of the designs that were out there. Some of them were to try to increase shield effectiveness. Sometimes they were designed to create higher power capability, but the RG numbers is the baseline for all coax even today. So to give you some insight, what does that mean? Well, RG8 is the baseline coax design for 400, 9913, you name it. All those different types of cables or those numbers realistically get designed off an RG8. 600, which is the big brother to it, is really RG17. The one that didn't make an RG number because the commercial program decided to take over was the RG8X. Now, technically it'd be an RG450 or in that neighborhood before they stopped. But realistically, when it was designed by Belden, they came up with the concept because of the mobile applications that they were trying to design it into. But the government decided to cancel the program, decided to let the commercial piece take over. So they just nicknamed it RG8X, which is a good bit of marketing because it is just a smaller version of an RG8. And the product took off from there. There's probably a lot more than you want to know here versus solid and stranded. So just a couple of highlights. Solid center conductors are still great for fixed mounted antennas. They're, if you've got a standard stationary stick antenna or a vertical, I always suggest maybe taking a look at a solid first. Now, there can be installation issues or other things that can make it challenging, but if you can make it work, you can increase your performance by having about 10 or 15% lower loss compared to a stranded counterpart. It can be a less expensive option because we can get creative and do a aluminum center with copper over it. And your shield effectiveness can be better because it's stationary. Now there are the trade-offs, which is the limited movements. So that's where the stranded types came in. Going to a rotor application, high flexing, things that are portable, things that are mobile, using stranded is always ideal. With the high flexibility though, nowadays you won't see too much impact as far as the overflexing that some people saw back 20, 30 years ago, because now that we have the way it's woven and the way we have the dielectric placed, you won't have a center conductor stray like some people had at one point in time. It's designed for small uniform bending. You can get down to inch and a half bend radiuses. And the way we've woven the bond for the foil has a high percentage of overlap. It's about 20 to 30% on the foil. So the shield effectiveness is improved. So still, even though there's a bit of a trade-off, some people still prefer the stranded, and that's okay too. So just to go through the popular coaxes for amateur radio, kind of just put a quick and dirty table up here with some insertion losses at different frequencies. But what it's designed to show you a little bit is, as the insertion loss can change, financially, there might be a trade-off where it may not be worth to make a change. So for example, everybody wants to go to the lowest cable, which is, in this example, the 600. But if you're at HF and you're at 10 meg or better, or even 30 meg or 50, is it really that big of a performance difference? And the answer succinctly comes down to no, because if you look at the three top ones, even with the 213 and the 8X size, when you get down to it, it's such a small delta that it may not be worth it to go to the bigger cables. So one thing to take into account is, using the right cable with the right insertion loss. And when that decides that it's not economically feasible, either looking at better antennas or looking at potentially an amplifier, even though those are trade-offs sometimes, those things can actually then help perform the overall system. So 600 is still very popular with us. Some people use it, for their base stations when they go above 200 feet, VHF, UHF above at usually about 100 feet or greater. We do sell still quite a bit of this for bidirectional systems and some repeater systems here. I know some people don't like it. They've heard that there's been issues with it. The challenge when this product was first designed was the connectors with the captivated center pins didn't hold with the finger springs, and another manufacturer had to change that design. And then another company that makes Heliax decided to use a marketing campaign to push against this. It's totally a preference thing. We still sell plenty of Heliax. We sell plenty of this product. And in reality, it's whatever works best for you as the user. But this is still one of those types of products that we see a lot of movement on, that a lot of people buy today. So getting back down a little bit, take the next step down, which is the 400 solid. Like I said, great for stationary antennas, low loss. It does have a slightly better jacket than your generic products that are out there, which is not only UV, but it's direct burial and chemical resistant. It's good on HF, but like I said, I usually don't recommend these types of products until you get to VHF and above because of some of the performance. Now, that being said, there's a lot of multi-banded antennas. There's a lot of multi-banded radios. So between the 400 solid, and I'm just going to jump to the flexible version, you can't go wrong with either one of those two products if you had a newbie that was starting off and wanted to get a cable that they could do other things with or have the most versatility. So that's generally the reason why these two products are so popular, is because between their lower losses, their shielding, and how they're designed, definitely can make it easier for people to say, what do I start with? Where can I start that might be future-proofed in a sense and can do the most with? So this is one area to look at. Now, these products that I'm talking about all have that gas injected foam. The reason why going to that makes sense is just because it's a matter of economics. It's really inexpensive to design it with that now. Between running the nitrogen line and the chemical foam, we've got the process down that it's about as cheap as it can get from a manufacturability standpoint. So it's very easy to design these with. Where the differences come in for a lot of it is in the braiding, how much braid you put on there, and then what type of jacketing do you use? Because like I said, you can add a few pennies into it, make things non-contaminating, which is burial, and just make it easy. As I mentioned earlier, 213, is it still viable? Does it make sense? And in a lot of cases, it still can. And the reason being is for HF applications where you're going 1 kW and above, getting into the legal limit, for two reasons. One is the average power that it can handle is certainly more than enough, but the solid poly dielectric actually handles the consistent heating and cooling better than the foam dielectrics do. It's got a higher melt temperature and it's a more robust extrusion, which means it's designed to be stiffer and thicker as it's gone through. So it still has the flexibility, but yet it's also designed where it won't have any RF scorching as it goes through a longer period of time. So what does that mean? An average cable's life cycle is designed for 20 years. This product was designed so well that it actually lasted 40 years. And how do I know that? Well, the folks at Belden decided to actually put one into a system and run it with a number of tests. They life cycle tested it. They took the product, they buried it for 40 years. They've done other things to beat up the cable and just recently brought it back up in 2017. And the product looked as good as it was back when they originally buried it 40 years earlier. So always something to take a look at. And the other reason why 213 is sometimes popular is because it also costs about 10 to 20% less than using a 400 type product. It's just food for thought. Now getting into some of the popular smaller coaxes that can be used in automotive applications, portable applications, other pieces. Two different types to kind of replace the 8X that I talked about earlier. One is the solid, which is just the standard 240 product. Nice for small stationary runs. It's nice and lightweight. It's great for systems 50 feet or shorter. So it's something that a lot of people sometimes overlook between that and the stranded just because it's smaller. But the one other benefit that it has to it is the dielectric loss gets it so close to the traditional RG8, which is twice the size, that it's a lot better than it used to be. And it's about 30 to 40% lower loss than the old 8X. Here's the solid and then the stranded version. So something to always talk about with people is if there's another next entry level coax, this would definitely be it, just because of the product's design, the low loss, the capabilities that it has for the flexing and twisting, and as far as the price goes, it's a little bit of a savings there too. One other quick comment for this is if you're not running any point in the shack where it's not hitting legal limit, I would strongly recommend using the 240 Ultraflex or something small in this size. even though we love to sell you the bigger cables, and there's plenty of places where you're running it after an amp and other places into meters and test equipment, is the smaller coax is going to be a lot easier to connect to the back of the radio and also to make interconnect jumpers. So I would say that this is one area that sometimes people get a little blinded by losses when it comes down to a 3-foot section. It's really hard to measure the difference between this smaller 240 Ultraflex 8X size product in comparison to running a larger 400. They're pretty much on top of each other. So, and then the last little cable to talk about today is the 316. This has gained a lot of popularity over the last, I would say, 3 to 5 years in the amateur community. A lot of people are doing the backpacking, hiking, doing something that they want a quick and easy cable to stick in a door jamb or into an apartment or some other application that they need something easily used. But the nice thing about it is it's small, it's lightweight because it's Teflon or PTFE. It can handle a decent amount of heat. It's not designed for long runs, but everything 25 feet, and above is just fine. I know I put 10 on there, but I can clearly say that we've used it in other pieces as well. And definitely the type of thing to take into consideration because it can be rolled, twisted, bent, rolled out, put back into place, and packed up, and away you go. The other nice thing about using this type of product is it is really hard to crush Teflon products because of the density of the design. So one definite place to take a look at. Couple of words to look for, maybe a little cautionary tales, is coax sometimes is not always built the same. Some people, get products with inconsistent center conductors, or the dielectric is supposed to be gas injected foam and it's either a bad foam or something else. There's a lot of tools to measure. A lot of people have TDRs, they've got those hand units, an SWR meter. There's a lot of ways that you can check the performance of it. Woven braid, it really doesn't cost a lot of money to change from a 65% to a 95% braid. Some places take shortcuts just because they're trying to shave a few pennies. Because I build, from my perspective, all my cable here in the US, it's easier just to make it fully the largest braid coverage, or as we talk through the compounds and the jacketing to improve upon it, than it is to take shortcuts. How do you tell? Well, check and see if they actually followed the RG standard. European modeling is important, but European cables were modeled off of the same RG standard here in the US. If they had special or different connectors used. Also, just so you know, testing, even though we love to say we'd like to do testing in metric, the imperial standard is really the test standard that everybody should be using, because you can be a little bit more exacting on the numbers. And then looking at those loss characteristics. So sometimes people put things in meters instead of feet, and just be aware. The last piece today real quick is the connectors. I'm not going to go through too much of this piece here, but we'll get into it. PL259s, still by far the most popular from an amateur standpoint. They've invented a long time ago. They were originally designed from coax when the government was looking for ways to make connections during World War I. And the design that was originally done has been redesigned several times. A couple areas. One is to accommodate the larger pins of the 400 material, tapering the center conductor to improve the performance. Sorry, guys. And then also looking at crimping connections for a stronger life of the connector itself on the cabling. The biggest challenge with this product was two areas. One is the impedance is not stable. due to the outer shell's movement. So there are some tricks that we've done there. And then the other thing is it can be difficult to weatherproof. So that's the reason why when you look at some of the products that are produced, a lot of times using these sealants on the back end is the best we can offer, but it still helps quite a bit. N types, originally for the government above 300 megahertz when everybody thought the world fell off. Extremely durable design. If I had my druthers, I would recommend N types just because they are a constant impedance between the center conductor, and you can see the rings in the shell. They have a minimal capacitance bump, and they're actually very good with dealing with intermod issues. And then the other nice thing is it's very easily to get an N-type to rate up to 18 gig. I know it doesn't apply always to the amateur use, but this is one of those preference things that you get a better product with. So, BNCs have they were very popular for a long time, especially with handhelds. They kind of fell off for SMAs, and they've gotten a lot of resurgence with a lot of the equipment out there. So I know the QRP market likes BNCs quite a bit. And I know that, a lot of other areas, there's still a lot of test equipment with it. The nice thing about the BNC is because of its high mating cycle, and it's easier to use over the N types for that, and they were much more difficult to break. So, the nice thing about the BNC is it can just twist, lock, and away you go. SMAs, the sub-miniature products, these became popular back in the 1980s, 1990s, and they were pretty much designed to replace the BNC and TNCs because of the way the design was with the threading, and the frequencies could go much higher and their low noise properties. I know a lot of HTs today are designed with the SMA connectors, the male or female. If I had my druthers, I'd like to see more of the male types out there, just because the female are locked with the threads. So you have to twist the HT onto the cable to make it fit versus having a locking nut that rolls through with the male. But that's just a personal opinion there. So a quick question, why BNC versus SMA? What happened? Obviously, like I said, it was a staple for the longest time. And when the SMAs came out, it was a little bit of the economics, but it was actually because the units could be made smaller. And with the SMAs being so popular on the wireless boom, it was an easy way to come over and become a major contender. And obviously with SMAs, we could use it on flexible cables as well as semi-rigid. BNCs have a ton of life. Do sell a lot of BNC on some of the cables that I build today for the different communication markets. But we also install a lot of BNCs for 75 ohm applications for HDTV, TV, and stuff like that for the broadcast market. So I still use a ton of them. Just a real quick thing on best practices. Obviously, look at the highest frequency and the distance on the coax. Sometimes numbers can drive people crazy. Look for places that make sense in the break in the lines for servicing feed lines. I know a lot of people say direct is best, one length works for all, but it can be a little misleading. If the coax has a problem or something else happens in the feed line, then you got to take the whole thing out of service versus a jumper on the inside that goes to a connection point, and then from there feeding up to the tower, and then using a jumper at the tower or at a lighting protector. Jumpers, like I said, can be a little misleading. Sometimes the smaller jumpers are more than adequate to take care of what you need versus the bigger stuff. Please take into account RF power equals heat. Can't tell you how many times people burn their hands. And then coax, for a lot of people, generally that's anywhere from 10 to 20 years, just based on usage, not so much that people are beating on these things on purpose. But it's, like I said, going back to the analogy in the beginning, which is it's a lot like road tires. The harder you are on it, the sooner that it's going to weather or wear out and needs to be changed. Don't get so hung up on exact match ratios. Sometimes it's uncommon to get to 1-to-1 in perfect applications. There's expectations and reality. More bands on an antenna can sometimes be harder to match. Antenna tuners are great. And then the last piece of advice is sealants are probably your #1 insurance on cable, coax. A lot of people just get a piece of coax, get excited about it. And in some applications where it's mobile or other areas, portable, you can't do this. But in a lot of places at base stations and stuff like that, a piece of sealants will save you a lot of time and effort from changing that coax a lot earlier than it was intended. Even we being in the wire and cable industry learn hard lessons. We had a piece of coax that was sitting out at one of the test areas, and we didn't realize it was close to a sprinkler, and we were taking it on, taking it off. And then next thing you know, we realized something was going wonky, and we found water right at the connector, and it had seeped into it. So sealing is a great piece of insurance. So that's it for the presentation. Hopefully this was helpful and you guys got a nugget of information or two, and I'll let you change it over and start some Q&A.
Great. Thank you so much, Chuck. Very fascinating. So this completes the presentation portion of the SNARS monthly meeting for February 5th, 2022. We're going to stop the recording and then we'll have the next section on Q&A.